When we usually prep for these deep dives, we find that the popular understanding of a topic is just a little bit simplified.
Right, yeah.
But when it comes to wireless signals, I mean, whether we're talking about setting up Wi-Fi in your home office or connecting a drone or even long-range radio, our mental model isn't just simplified. It's fundamentally wrong.
It's a cartoon, honestly. We tend to think of wireless data like a laser pointer or maybe a string pulled tight between two tin cans.
Exactly. The assumption is basically if I can see you, I can talk to you.
Yep.
If I point my antenna at your antenna and there's nothing physically touching that invisible line between us, we are good to go. It's that line of sight logic.
And that logic is the single biggest cause of frustration in network engineering. Because in the real world, physics doesn't travel in a one-dimensional line. It travels in a volume.
And that is the aha moment we're chasing today. We are looking at the Fresnel zone.
Pronounced Fresnel or Fresnel, depending on which engineering professor you ask, of course.
Yeah, I actually saw that debate in the sources. But however you say it, the concept is the same. We need to completely reshape how we visualize the air between two antennas.
We really do.
We need to understand why a tree that is 20 feet away from your line of sight can still kill your connection. And why, and this was the part that really blew my mind in the research, a smooth grassy hill is actually a more dangerous obstacle than a jagged Rocky Mountain peak.
Yeah, that Campbell scientific data is a real head-scratcher until you understand the wave mechanics behind it.
So let's start at the beginning. We have this stack of research from Telecommunication Electronics, Cloud RF, some pretty heavy technical briefs from circuit design. They all start by dismantling that laser pointer myth. So if the signal isn't a straight line, what does it actually look like?
I want you to visualize a shape. If you have a transmitter at point A and a receiver at point B, the signal doesn't just walk the line between them, it expands.
Okay.
The source from Telecommunication Electronics describes it as an elliptical, three-dimensional area.
When I read that, the image that immediately popped into my head was an American football.
That is the perfect analogy. Or a blimp. Or a capsule.
Right, so it's pointing at your router, it's pointing at your laptop, but in the middle of the air, it bulges out. It gets fat.
Exactly. That bulge is the Fresnel zone. It is the physical volume of space that radio waves occupy as they propagate. They don't just stay in a lane, they spread out.
And it's not just one single shell either, right?
Right, yeah.
The literature describes it almost like an onion.
Right. Theoretically, this expansion goes on forever. You have the first Fresnel zone, which is that core football shape. Then wrapped around that is the second zone, then the third, and so on out to infinity.
But for the purpose of actually getting Netflix to load for you, the sources seem to agree that we can ignore the outer layers of the onion.
For the most part, yeah. The circuit design notes are very specific about this. The first Fresnel zone, that innermost football, contains roughly 90% of the signal's energy.
So that's the payload.
That's the payload. If you keep that first zone clear, you're usually in business. If you mess with that zone, you start losing data.
Okay, so we have the shape. It's a 3D football made of data.
Nice way to put it.
Now we have to get into the physics of why this matters.
Right.
Because this is the part that I think trips people up. If I build a brick wall between two antennas, obviously the signal stops. That's just intuition.
Right. That is a blocked path.
But the Fresnel logic says I can have a clear visual line to the other antenna. I can literally look through a telescope and see it perfectly. But if a tree branch is poking into the side of that invisible football, my signal degrades. Why? The branch isn't touching the direct path.
Well, this is where we have to stop thinking about particles and start thinking about waves. Radio waves are not bullets. When they leave an antenna, they radiate. They want to take every possible path to the receiver.
So you have the direct wave going straight down the middle, the laser line.
Correct. But you also have secondary waves spreading out to the edges of that football shape. Now imagine one of those secondary waves hits that tree branch you mentioned.
It bounces.
It reflects. It hits the branch and bounces back toward the receiver. But think about the geometry here. The direct wave traveled a straight line. The reflected wave went out to the tree and then to the receiver.
It took the scenic route.
Exactly. It traveled a longer distance. And because it traveled further, it arrives later.
And this is where the trouble starts.
This is the mechanism of failure. It's called phase cancellation.
Okay.
Radio waves are cyclical. They have peaks and valleys, ups and downs. If that reflected wave arrives just a little bit late, specifically if it travels half a wavelength longer than the direct wave, it arrives out of phase.
So when the main signal is zigging, the reflection is zagging.
Precisely. The peak of the reflection hits the valley of the main signal, and mathematically they don't just mix, they subtract.
They cancel each other out.
The source from Learn Everyone calls this Fresnel zone interference phenomena. That reflected wave basically acts like a sniper. It takes energy away from your main signal. So that tree branch isn't just a passive object sitting nearby. It is actively mirroring a cancellation signal back at you.
That is wild to think about. You're not just losing signal because it's being blocked. You're losing signal because it's being attacked by its own reflection.
Exactly. It creates a dead zone at the receiver even though your eyes tell you the air is clear.
This really clarifies the terminology I saw in the TCON electronics brief. They broke down the different types of connection scenarios. LOTAS, NLOS, and LOS.
The acronym SOUP of network engineering.
But it's important SOUP. So LOS is line of sight. That's the dream scenario.
Right, the visual line is clear and the Fresnel zone is empty, zero obstruction.
Then you have LOS, non-line of sight. That's the brick wall scenario.
The zone is blocked, the visual line is blocked, you aren't connecting.
But the dangerous one, the one that tricks people, is the middle one. Small n, capital L, OS, near line of sight.
This is the silent killer. Near line of sight means you can see the destination. The visual path is open. But that invisible football is dragging its belly on a roof, or grazing the side of a building, or hitting that tree branch.
So you have a visual connection, but a radio disconnection.
Or at least a severe degradation. You'll get packet loss, buffering, dropped calls, and you'll be standing there looking at the antenna thinking, but I can see it.
Now, surely the thing doing the blocking matters, right? Casualty is different from a rock, which is different from a metal roof.
Absolutely. The material is huge. The Learn Everyone source specifically calls out water and trees as the arch nemesis of 2.4 gigahertz signals, which is your standard Wi-Fi.
Because trees are just vertical sticks of water.
Biologically speaking, yes. Water is fantastic at absorbing radio energy. So if your Fresnel zone hits a dense, wet forest, the signal doesn't just bounce, it gets absorbed, it just dies.
But here's the paradox that I really want to unpack. We talked about it in the intro. The Campbell scientific data compares two types of terrain obstructions, a night edge and a smooth earth.
This is one of those facts that really separates the pros from the amateurs.
So picture this. You have a signal path blocked by a sharp, jagged Rocky Mountain peak, a knife edge.
Yep.
And then you have a signal path blocked by a gentle, rolling, grassy hill. Intuition says the hill is better, it's soft, it's round, it's grass.
And intuition is totally wrong.
Why?
It comes down to how waves handle edges. When a radio wave hits a sharp edge like a rocky peak or the top of a building, it undergoes knife edge diffraction. Think of it like a pivot point. The wave hits that sharp tip and bends around it. The Huygens-Fresnel principle basically says that the edge becomes a new source of radiation. The signal spills over the wall and you can actually pick it up on the other side.
So the sharp rock helps the signal bend.
It allows it to continue, yes, but a smooth, curved surface, like that gentle hill.
The Campbell report says it can totally obliterate the signal.
Because a smooth cylinder doesn't give the wave a sharp point to pivot around. Instead, the signal grazes along the surface. It gets scattered, absorbed, and diffused in a dozen different directions.
So the friendly hill is actually a signal black hole.
Essentially, the diffraction loss on a smooth sphere is massive compared to a sharp edge. So if you have to choose between a jagged rock and a rolling hill to block your signal, pick the rock every time.
That is such a counterintuitive takeaway. It really reinforces that we are dealing with physics, not aesthetics.
Exactly.
So we know the shape, we know the interference risks, and we know the obstacles. But we live in the real world. We can't always have a perfect empty void between antennas.
No, and you don't need perfection. That's the good news.
We need a rule of thumb. How much of this football needs to be clear?
The industry gold standard cited by both Campbell and Circuit Design is the 60% rule.
The magic number.
You don't need 100% clearance. The physics is forgiving enough that if you can keep 60% of the first Fresnel zone radius clear of obstructions, your signal loss is basically negligible.
So if my football is 10 feet wide in the middle, I need to keep the inner 6 feet clear.
Roughly, yes. If you maintain that 60% clearance, the connection behaves almost exactly as if it were an open space.
But what's the cost? If we violate that rule, let's put some numbers on the pain. If I encroach into that zone, say I'm only 40% clear, what happens?
Then you start bleeding decibels. The Campbell scientific source gives us a really stark breakdown of the keep-out costs.
Walk us through the damage.
If you are obstructed beyond that 60% mark, so the visual line is clear but the zone is crowded, you can lose up to 6 dB of signal strength.
And for anyone who doesn't live in the world of RF engineering, is 6 dB a lot?
It's massive. Remember, decibels are logarithmic. A loss of 3 dB is cutting your power in half. So a 6 dB loss, you have 1/4 of the signal power you should have.
Just because a tree is near the line.
Right. And it gets worse. Remember that knife edge obstruction? If that rock is just barely grazing your visual line so you can see past it, but it's touching the laser beam, you lose up to 14 dB.
That's huge.
And if the zone is fully blocked, you're looking at greater than 20 dB loss. At that point, your data isn't just buffering, it's likely gone entirely.
Okay, so the stakes are high. We need to clear the zone. But let's get into the solutions mode. Because sometimes you can't move the obstacle.
Right. You can't move the mountain and you can't cut down the neighbor's tree. We have to engineer around it.
There was a scenario in the Cloud RF source that I absolutely loved. They called it the farm problem.
Oh, this is a classic narrative. It's the perfect way to visualize the variables we have to play with.
So paint the picture for the listener.
Okay. Imagine you have a transmitter up on a hill and a receiver across a river valley. You have a beautiful, long visual line of sight. But down on the valley floor, right in the middle of the path, there is a farm.
Barns, silos, maybe an orchard.
Exactly. And because the distance is long, your Fresnel zone, your football, is fat. The bottom of that football is dragging right through the barn roof.
So the signal is hitting the farm. What do we do? The most obvious answer seems to be build a taller tower.
That is variable number 1, height. If you raise the antennas on both sides, you physically lift the entire football shape up into the air. If you go high enough, the bottom curve clears the barn and you're back to full signal.
But height is expensive. Towers cost money. Permits are a nightmare. What if you can't go higher?
This is where the physics gives us a magic trick. Variable number 2, frequency.
This was the part of the research where I actually stopped and said, wait, really?
It's true. The size of the Fresnel zone isn't fixed. It depends entirely on the frequency of the wave.
So the football shrinks and expands.
There is an inverse relationship. Lower frequencies have longer wavelengths. Long wavelengths create a large, wide Fresnel zone.
So a low frequency is a fat football.
Think of a bass note from a subwoofer filling a room. It's big. So in our farm problem, if you were using a 900 megahertz radio, your zone is huge. It's definitely hitting the barn.
Okay. But what if we switch radios?
If you jump up to a higher frequency, say 5 gigahertz or even higher, the wavelength gets shorter. And as a result, the Fresnel zone gets tighter.
It sucks in its gut.
It becomes a skinny football. And here is the magic. That same signal path at the exact same height might now squeeze right over the top of the farm without touching a single shingle.
That is incredibly cool. You didn't move the tower. You didn't move the farm. You just changed the math of the wave, and suddenly the obstacle doesn't matter anymore.
It's a really powerful tool. Now, full disclosure, there is a trade-off.
There's always a catch.
Higher frequencies don't travel as far generally, and they are much worse at penetrating solid objects if they do hit them. But specifically for clearing a Fresnel zone, going high frequency is often the smartest move.
And there was one final variable that dictates the size of this zone. Distance.
Distance is the enemy. The radius of the Fresnel zone increases with the distance between the antennas.
So the further apart we are, the fatter the football gets in the middle.
Exactly. It's simple geometry. If you shoot a signal 1 mile, your zone might be 20 feet wide. If you shoot it 10 miles, that zone might be 60 or 80 feet wide.
Which means obstacles in the middle of a long link are way more problematic than obstacles near the ends.
Correct. If you have a tree near your antenna, the zone is still skinny there. It hasn't bulged out yet. You might miss it. But a tree in the exact middle of the path, that's where the zone is widest, that tree is going to cause maximum damage.
This really changes how I look at those microwave dishes you see on cell towers. It's not just point and shoot. It's a volume calculation.
It's 3D geometry. Every link is a calculated tube of air that has to be kept clean.
So let's bring this all back together. We've covered a ton of ground or air, I guess, in this deep dive.
We really have.